Amaury Hayat from Ecole, and she's going to talk about how artificial intelligence affects.
Thank you. So I'd like to start by thanking the organizers for the invitation. It's an incredible pleasure to be here this week, and especially as the talks so far, at least, have been very interesting. So my name is Amaury Hayat. I am a professor at Ecole, part of the Institut Polytechnique de Paris, and I'm going to try to present you part of my research, which is essentially with the theme of this week, that is, how can artificial intelligence help mathematicians? So, of course, there has been a lot happening in machine learning in the last few years, but I'd like to take a step back and try to see how the world was like 5 years ago. Well, 5 years ago, we were already using AI tools on a daily basis, but most people either didn't realize it or didn't think of it. And if you're in this room today, it's probably that you were aware of it, but most people weren't. Now, of course, all this changed, and since 2022, we've seen kind of a social revolution where hundreds of millions of people are every day using AI tools knowingly, and mainly thanks to these tools that we all know, and none of these existed just 3 years ago. So we went from a computer scientist awareness to a global awareness, and when I say global awareness, I include scientists from other fields, including mathematicians in it. Today we are in a situation where I think the youngest Nobel laureate in chemistry in history is primarily a computer scientist. So AI is changing the practice of science, and so of course it's natural to wonder how is it going to change the practice of mathematics. Now, when I started working on this like 5-6 years ago, I can tell you this was a crazy question to ask to a math department, at least to my math department. But you know, the situation has changed in the last 5 years, and this idea has started taking roots, and more mathematicians are asking themselves, how can AI help mathematicians? And I think that's exactly the reason why we are here today. So usually when people ask themselves these questions, and they're mathematicians, the first thing they do is to try to use a large language model and ask a question to either ChatGPT, Gemini, Mistral, your favorite, and ask, for instance, to prove a small thing. And if you were to try this in 2022, 2023, you would usually get terrible answers, like so-called hallucinations, but essentially things that didn't make any sense from a reasoning point of view. But the models are evolving quickly, and if you try today with the so-called reasoning models like O1, O3 from OpenAI or R1 from DeepSeek, you might actually get things that are interesting from time to time. For instance, this is a screenshot of a paper I'm working on in my original field, in control of PDs. This has nothing to do with AI, but except that there's a small lemma at some point about differentiating a function that depends on the determinant. And I wanted to show something about that, and I asked O3 mini high the proof. So the proof is twice as long, actually. It just didn't fit on the slide. And after 2 questions, the proof was correct. So, I mean, it's not super duper. It's like something that I would have done in an hour and a half. But still, in 5 minutes, this was done. So there are already things for which generic tools that you will find that you will find very easily that are already useful. There are also other basic usages that for which people are using generic LLMs. I'm taking this opportunity to remind that using it in a reviewing process is forbidden for most journals and conferences. But this is really not what I want to talk about today, because today I'd like to see how we can go further than that. How you can do more than just using generic LLMs to improve AI, to improve mathematics with the help of AI tools, still with language models. And so in my opinion, there are essentially 2 branches. The first one is using AI tools for math discovery. So you're using the AI as a tool. You're not asking it to do any reasoning, but you want it to, at the end of the day, output something that is either a candidate solution, a candidate conjecture, or has an intuition that is much better than you would have had on this particular problem. The second one is automated theorem proving. And then in this case, you are actually using the AI to show something, and you want the AI to output a correct proof of a statement you're giving to it. So I'll talk a bit of both. I'll start with the first one, AI tools for math discovery. And because it's 9 a.m., I'll start with just a story, and by saying that solving math problems with a computer is something that we have been doing, in fact, for a very long time. Some of you are completely aware of it. For some of those, for some others, it could be a surprise. But my favorite example is this conjecture by Euler of 1769. So of course they didn't have a computer at the time. Euler thought that if there exist integers a1 to ak and b such that if you put the k first to the power n and sum them and it's equal to the last one to the power n, then k has to be larger than n. N has to be larger than something, but. And Euler wasn't able to prove this conjecture during his life, and actually this remained an open problem for almost 200 years, meaning that no mathematician was either able to prove or disprove this conjecture. So this was until London and Barkin arrived in 1966, and they managed to show this, to solve this problem in the most silly way you can think of. They just used a computer to try many possible combinations, and they found this. So you see that you have 4 integers here, you have 5 here. So if you go back to Euler's conjecture, if it were true, 4 will be larger than 5. Okay, we all know this doesn't work. So this was a new mathematical result. But most importantly, it's one of the only math papers that I know of that can fit on a single slide. So, of course, there have been much more involved examples, like the proof of the last case remaining of the Cayley's conjecture, where essentially you can reduce the proof to many cases to check, but the many cases is far too many for a human, up to the point that at the end of the day the proof is around 200 gigabytes. So if you want to read it out loud, it's going to take a while. We've seen this week already several impressive results using SAS solvers. So at the end of the day, using computers to prove theorems is something we have been doing for a long time. But the question is now, can we do more than a high number of case checking? Can we do more than what we were doing before? And can AI be useful to solve more complicated problems? So I'm going to try to convince you that the answer is yes, and I'm going to try to do this on 3 different examples using different types of neural networks. The first one is the stability of dynamical systems. It's in the field of dynamical systems, and it's the example that was presented yesterday during the tutorials by Sean. This was the first paper he was talking about. So discovering the Lyapunov function. So let's start with a bit of context. We're going to consider a system of differential equations. So you have x prime is equal to f of x, and because we're mathematicians, we need to specify a few things. So there will be n equations. F has to be C1. F of 0 is equal to 0, meaning that 0 is in equilibrium, because if you start at 0, you remain at 0. X prime will be equal to 0. And what you would like to know is what we call the question of the stability. You would like to know whether it is true that for every epsilon, there exists a delta such that if your initial condition is lower than delta in norm, then your solution exists for any time, and in addition, it remains smaller than epsilon. And if this is true, we say that the system is stable, but in other words, it means that solutions are arbitrarily bounded if the initial condition is sufficiently small, and if you want to draw this, you would like that for any red ball, there exists a blue ball such that if you start in the blue ball, you have no idea what the solution is doing, but at least you know it will never exit the red ball. That's essentially what you're trying to show. So this is a question that has been studied for a very long time. I mean, if you look at the fancy examples, you can think of the work of Henri Poincaré, notably with the 3-body problem. And it has interested mathematicians for a long time. And thanks to Liu Xinqin and Netflix, it has also interested the general public for about 3 weeks last year. So in this area, there was a significant advancement at the turn of the 20th century. And these were the Lyapunov functions. What Lyapunov showed is that if you want to study this complex problem, a sufficient condition, and actually necessary in most cases, is that there exists a function such that this function is strictly minimum in 0, your equilibrium. It goes to infinity at infinity, and you have this weird condition between the gradient of the function and the dynamic of the system. And if you can find such a Lyapunov function, then your system is stable. You know that for sure. So it's a very powerful theorem because it reduces essentially the complicated question of studying the stability of a system and what are doing all trajectories to finding this kind of hidden energy of the system that is a Lyapunov function. There is just one tiny little detail missing, which is that nothing tells you how to find such a Lyapunov function. And in fact, this is not completely a detail because it's not a simple problem. For instance, if I give you this system and I tell you, so I can tell you there is a Lyapunov function. Can you try to find a Lyapunov function for this system? I mean, can you try to find a kind of energy that decreases along the trajectories of this system? I thought someone was... Okay. And in fact, this example, as surprising as it may seem, is not a complicated example. I mean, you see, if you look, there is one possible Lyapunov function. There is no cross term, so it's a polynomial. So first, it's easier, but there is no cross term. You don't have like x1, x2. So it's relatively an easy example. And even for this, it's not completely obvious. It's such a complicated problem that today it's perfectly decent to have a very good paper saying this class of system has or doesn't have a Lyapunov function. So today, more than 100 years later, it's still an open question. There's still no systematic way to construct a Lyapunov function, and there might never be, actually. So what do we do, mathematicians, when there is no systematic way of solving a problem? Well, usually we resort to intuition. So intuition is an important concept in mathematics, and most of the time, it resembles a kind of pattern matching. So you've seen many cases that look alike, this one, but it's not exactly this one. So it gives you an idea of how to proceed in this case and what to try. But we know that neural networks are extremely good at pattern matching. So a natural question, at least from my point of view, will be, can we train an AI to have a better mathematical intuition than us? Right? I mean, it might make sense. So this is exactly what we tried, training an AI to get an intuition of Lyapunov functions. And the goal was, so this is just to remind you the goal. The goal is like I give this system to the neural network, and I want the neural network to output, optionally yes, but I want the neural network mostly to output a Lyapunov function if there is one. Why do I want to output the Lyapunov function, just not an answer? Just because I don't want to be able to have to trust the neural network. There could be hallucinations, so I really want something that I can actually check at the end of the day. All right, so this is what we did with Alberto Alfarano and François Charton. So we started in 2021 actually, and then ended up in 2024. So they are both researchers at MetaAI. And what we used is a transformer, so exactly as Sean was presenting yesterday in the tutorial. But the transformers we're using are very small. They are of the order of magnitude of 100 million parameters, so essentially 1,000 times smaller than GPT-3, for instance, the original one you had in the original ChatGPT. So the procedure is relatively simple in principle, but then each step might be more harder. So the first one is to generate a set of systems and associated Lyapunov functions. You want to train and supervise learning your transformer, so you will need examples and solutions, right? You need something to train it. And this is the hardest step. Why do I say it's the hardest step? Because how do you create examples when you don't know how to solve the problem? So you can't really just sample systems, solve it, and then you get your examples. I mean, if you can do this, there's no point in training the transformer. So what we did was, using the backward approach, we sample the solution, and then we create a system for which this is the solution. Right? It's the only thing we can do and the only thing we know how to do. So in this situation, it means that you're going to try to find a mathematical way to get a function that is strictly minimum in 0 and goes to infinity at infinity. And then you're going to sample systems for which this is a Lyapunov function. So in Spirit, we're using the fact that one direction of the problem is much easier than the other, and we want the neural network to learn the hard direction, the one that mathematicians are interested with. But of course, there are limitations, because even if you had a perfect generator, which is never the case, but even if you had something that can perfectly represent all positive random function that goes to infinity at infinity in all systems for which this is a Lyapunov function, you will still bias the distribution by this way of sampling. So it means that you need to be very careful when you test your neural network at the end of the day. You need to test it on something completely outside of distribution that looks like, you need to test it on problems that looks like, if I may say, real-life mathematical problems like the one you will find in a textbook, essentially. Because you want to make sure that you learned the math problem behind and not the generator. And actually in this paper, the very first generator we had, after a year and a half, so we thought it was a great generator, the AI was training and so on, and when we tested the AI at the end, we had 95% accuracy on the training distribution and 8% accuracy on the test distribution, which shows you that you learned the generator, which is exactly what you don't want. Sorry. So, yes?
You're going to generate samples.
Yep.
And you only hope, I would say, is to solve those samples from the same distribution.
No, you hope to solve it for a larger distribution, but with the same base function. I mean, if it has never seen a cosine before, it will never output a cosine.
But it's possible with some work that you could generate examples of the distribution that you're interested in.
Well, in backwards, it's still relatively hard because, for instance, if you're doing something like this, just a basic thing, which is that your systems will be longer in average, just because you have you're taking a Lyapunov function, you're going to compute the gradient, you're going to try to construct something that is orthogonal to the gradient, except for a few components that decreases.
So this particular method, but in general it's possible.
In general it's possible. If you have a good backward methods that give you something that is the same distribution, I'd say yes, that's the perfect case. Yeah, that's the perfect case. And then you don't have to, you still have to make sure you're not learning the generator, but you'll probably see it completely quickly. In this case, you just have to make sure your generator is not too templated. Because if it's too templated, it's going to learn the generator. So then once you've done this, starts the easy part. The easy part is to encode the examples. So for mathematical expression, an easy way of encoding it and putting it to a transformer, as we've seen yesterday during the tutorials, is to enumerate, so to represent mathematical expression as a tree and then enumerate in whatever topological order you like. And then you just need to remain consistent. And then you feed these to the transformer. The transformer is actually going to send you something exactly like this in output, and then you can reconstruct the mathematical expression. And so then you can train the model in supervised learning. This is extremely classical, and if you have a doubt, you can look at yesterday's notebook by Sean. They're very well made. So if you try this, for this problem, the result is that it works, and amazingly, the AI learns the mathematical expression of the Lyapunov function. The funny story is that I said 2020, we started in 2020. When we started seeing the first results, we thought it was too good to be true, so we stopped for 2 years, thinking like, no way it works. And then 2 years later, there were more works on the transformers that were amazing as well, so we thought, oh, actually, maybe it was working. And then we started for a good year and a half. So it works exceptionally well if you had a priming approach. So this is just a technical detail. It's even better if your distributions are very different. You can take a little bit of your test distribution, so you're not going to test on this little bit anymore, but you add it from time to time in the training, and it gives something that is very different, and it forces the transformer to learn that there is something different. What's surprising is that actually just 50 examples out of 1 million start to make a difference. So we use 200, but still 50 is enough to start to make a difference. Anyway, so this is essentially the result you will get. And when I told you there's no systematic way to find a Lyapunov function, I've been lying a little bit because there are particular classes of system for which there is. This class of system are the polynomial systems where you can find a Lyapunov function that is a sum of square. In this situation, you can use sum of square solvers based on semi-definite programming to actually find a Lyapunov function. In principle, these solvers will get 100% accuracy, but then it depends on the size of the system because they tend to take very long and to consume a lot of memory. So at some point, you need to put a timeout and limit in memory. Here, we put a timeout of 1 hour and 2 GB of memory per examples. Someone told me, and that was true, that our AI is turning on 16 GB of memory, so it's not fair. I kind of agree. So we'll need to retry with 16 GB. Anyway. You see here that, so this is the training distribution, so the one that is biased. Of course, these are examples that has never been seen during the training, but still it's the same distribution. Of course, if you do your job properly, then the AI gets 99% of accuracy in this. What's interesting is the second line. It means that on these systems, that is a distribution that you will find rather in textbook, it still gets 84 to 93% of accuracy. And the nice thing is that it works for non-polynomial systems for which we really have no generic method, except in very, very particular cases. So these were extremely good performances, and the reason why I'm saying these are extremely good performances is that I wanted to try, how hard were these problems of 2-3 equations. And so I sampled them at random and gave them as a test to my master students. I have very good master students, but they still only got 10% accuracy. Then I tried on myself just to see, just to check, and I got 25% accuracy. So I feel like 84 is probably better than, if not any, most human on Earth in finding a Lyapunov function. But if you think you know someone who would like to compete, I'd be very happy to organize a duel.
Within 1 hour constraint?
So actually, yeah, we could do a bit better than that because there wasn't a 1 hour constraint for 6 problems. So you could do 1 hour constraint for 2 problems or for 1 problem. Yes?
For like strange attractors?
So we tried on a few particular examples.
Simple as like the Hanon, but that's discrete. That's not a differential equation.
No. So yeah, right. We tried on discrete, and we tried on a few ones that were indeed complex attractors that did work. I think like.
Did it work
With the Hanona attractor?
I didn't try this one. Could be good to try.
When the orbit goes around inside the attractor, the eigenvalues move unpredictably all over the place, even though it's quadratic. Sometimes they're squeezing in both, and that's
Yeah, that will be very interesting to try. In all these systems, the linear system is you can't decide with it's global stability, of course, but even locally, for most of these systems, you can't decide just using a linearization and Kalman criterion, just because you get zeros everywhere. Because those systems are usually strictly more. I mean, the linear system usually not exponentially stable at all. But indeed, we could try on more complicated systems. These were part textbook, part generated at random, but in a forward direction, meaning that you sample a lot of systems. You try to see whether a source algorithm with a very, very long timeout and a memory requirement gives you an answer. So it means that you throw outside 98.5 or 99% of your systems, which means that it's extremely costly to generate. But if it's to generate a test data set of 3,000 examples, that's okay. If you just can't generate a training distribution of that. I mean, it's. So yeah, there was a paper on the New Scientist. I'm just put it here because the funny part is that there was a paywall, so it took me 2 weeks to understand what was written in this paper. More interestingly, there is a Japanese YouTuber who decided to do a video on this paper. So because I don't speak Japanese, I can't tell you whether this is helpful or not. I've heard that this is a story of a fisherman that tells his granddaughter what a Lyapunov function is. But if you speak Japanese and you have a feedback, I'll be very happy to. So it's written there are subtitles, but they're also in Japanese, so it didn't really help. Okay, so just a summary of the approach is trying to train transformer to have a mathematical intuition of the problem, and the two key points are we try to generate data in a backward fashion, and then we test out of distribution on real instances of the problem. This is really important to make sure that you do learn the math behind. This framework has been used in many frameworks. We've seen 4 examples with Sean's talk yesterday. And if you want, you can try it yourself and customize it. It's relatively easy to customize on your favorite math problem. Then you just have to, the training code then is the same. You could replace Hayat 16 by Facebook research. The only thing is that I tried to put a collab on this fork that I created this morning. The collab notebook is so far extremely basic, but I hope it's going to get better in the next 2 days. You know, I saw the collabs from yesterday. I was so amazed that I tried to do one. Yes.
Yeah, so I have a question. So you first said that your AI learned a generator, so that was not a good thing, and then you showed good results, but I didn't catch what exactly was the step.
We reworked the generator. It just means the generator was too templated. So there were many places in the generator where, because there was no randomness, or because something was off, for instance, if you try to get in the system the parts that will contribute to decreasing the energy and the parts that don't contribute at all, for some reason, the part that did contribute for polynomial system, they had a degree in average 1.6 times higher in the way we had created the generator. So it's still an indirect signal that the transformer might catch.
But then what did you rework? Like, what was, like, how did you change it?
Oh, there was no AI involved in creating the generator. I just tried a bunch of equations and tried to see how you can try to analyze the distribution by hand and see how the distribution will be. You will avoid things that were obviously a signal of something. So for instance, you could say a very simple thing to do if I have a function is to take the system minus gradient of the function. Right? Because if you take gradient of this times the gradient of the function, it's going to be minus gradient square norm of the gradient square, so it's negative. But if you do this, you'll never generate anything else than gradient flow systems. And so that is going to be less interesting. So what we had was a problem like this in slightly more elaborated. And so we had to rework the generator to make sure it was really not templated and could at least sample things, even rarely, but at least sample things very far away in the distribution. Yes?
Do you test on any problems where you aren't generating the problem from the solution? Like, do you have any test cases where you did not go backwards?
Yeah, exactly. Actually, like the middle line, none of these systems were generated backward. Yeah, that was the main point. We were really testing on something that is not generated backward. Otherwise, it's only partial information. Right, so I'm going to try to move on to the two last examples. I'm going to be shorter on the two last examples, but now we're going to deep dive in applied mathematics to talk about the control theory and the control of mosquito population. So you have a system modeling mosquitoes. So you have eggs, male, females, and sterile male. And you have a control on the system, meaning that there's something in the equation that you can choose. It's the u here. And you would like to choose u in order to achieve a certain goal. Here the goal is to eradicate the mosquitoes. So what you can do is release sterile mosquitoes, and the hope is that because the female won't discriminate between male, regular male and sterilized male, sometimes they will make the wrong choice and then the population will decrease. The only thing is that this is a physical problem. It's something coming from nature, so you can't do everything you want with the control. First it has a max value, but in addition, we can't measure everything in this system. It's unpractical. What we can measure is the total number of males from time to time, and the total number of females, the one that chose a regular male and the one who chose a sterilized male. And so what you would like to do is to choose a function f such that the population of mosquito goes to 0, except maybe for the sterilized male. But because we are mathematicians, we'd like the population to go to epsilon as small as desired. So we stop at 10 minus 4 mosquito. The people in biology told us it was fine. So solving this question, finding an f, is an open question. It was brought to me by a famous researcher in control theory. And this was something that people weren't able to solve. And so we thought, okay, can we use an AI approach to suggest a control and see if it works? So the approach is relatively different from the previous one. What we did was transform the equation and discretize them using a well-chosen numerical scheme. Train a reinforcement learning model, so the relatively basic reinforcement learning model. And if it does work, the reinforcement learning model will give you a numerical control, meaning a black box. You give it numbers, it outputs numbers. And in simulations, on the discretized system, it gives something where the population of mosquito goes to 0. And there starts the job of the mathematician. It's to try to understand in this black box, what does it mean from a mathematical point of view? And what's useful in the behavior of this black box for the mathematical system. And then you can check that you actually got a solution of the system if you are able to recover an explicit mathematical expression of the control. So this is what we did, and so this is what we did. We trained the reinforcement learning model, and this is what we got. So we got so the control trained. The reinforcement learning model gives you a numerical control, and this is the numerical function. You have. So I told you we're looking for a function f, so that has two variables. So the first one is total males, the second one is total females, and this is the value of the function f. So the only problem is that when I see, I don't know for you, but when I see this, I essentially don't see any mathematical function that really completely stands out of the way. But fortunately, I had a very good PhD student at the time who directly realized that you need to look at it in log-log scale. And in log-log scale, indeed, you seem to have a region where you have maximal value, 0, and then a small transition in the middle. It happens that this PhD student is now affiliated in Berkeley, and I think he's in the room somewhere. Yeah, he's here. So if you do this, then you can look at what it means from a math point of view as a control, and then starts the job of the mathematician. You'd like to understand what's important in this. It turns out that the part that is important is very small. It's like this one. But this is still an expression that I would never have guessed just looking at the system. You see, your measures are here. Those are the variables of the system, of the solution. So you have a weird if condition with respect to the solutions of the system. And the funny part is that it actually works. So if I represent the trajectories with total number of males, total number of females, this is in red is the trajectory. It's going to oscillate, and then at the end of the day, end up at like 10 to the power 0 mosquito, which is fine for applications. You started from 1 million mosquito anyway. What's interesting is that this works for any epsilon larger than 0, but it doesn't work for epsilon is equal to 0. So I find it very nice that with something as approximative as neural networks, you can actually recover a kind of a mathematical bifurcation with this AI augmented intuition. So a reviewer asked us, does it work if you assume that you don't know perfectly the parameters of your system? And the answer is yes. So the control is, as we call it in control theory, robust in the sense that it can be useful in real life. All right, so this was for the second example. I'll be relatively quick on the third one because we've already been seeing it. Because the first thing I wanted to talk about is pattern boost. I don't even know if I need to talk about this slide, but Nevertheless, I'll do this for a couple of seconds. So this is the paper we've already heard about by François Charton, Jordan Ellenberg, Adam Wagner, and Jordi Williamson. And indeed, the idea is to couple to couple a transformer to an optimization algorithm, and you try to create good constructions from your classical algorithm from random seeds. You train the transformer on the best of such constructions, and then you use the transformer as seeds again for the classical algorithm, and then you repeat this. And at the end of the day, you hope to have constructions that are better than the one you had before. And so indeed, it allowed to close the Graham-Harary conjecture of 1992 using this method. Another example that looks a bit like this one, but slightly different, is an example in applied mathematics again, in optimization theory. So the goal here is to answer a complicated optimization problem, for instance, a dynamic routing problem. And for these, people had existing combinatorial optimization algorithm. Some other people tried neural networks, but what Leobati, Jungel, Klein, Parmentier, and Max Schiffer did in 2024 was to try to couple both and to put a neural network with a layer of combinatorial optimization. And instead of doing both separately, they trained all at once, like end to end. And by doing this, they ended up having a mathematical algorithm that was better than, an algorithm better than any existing mathematical algorithm and machine learning algorithm. And they won the Euroneurids challenge in 2022. So in pure math, it's extremely useful. In applied math, it's also extremely useful. All right, so there are many other examples. In topology, there was a famous paper by Alex Davis and the team of Jordi Williamson, so a team of DeepMind and a team in Sydney, who used feed-forward and message-passing neural networks to guess links between different quantities. Essentially, the spirit is if you have two properties of mathematical quantities and you'd like to know whether there's a link between the two, you just can try to predict one from another with a neural network. And if the neural network has non-zero good answers, it means that there is a link somewhere, and then you can try to attack the neural network to understand what the link is. So it allowed them to get a link between hyperbolic and algebraic invariance of nodes, and this conjecture was later proved. In partial differential equations, there's a team which used physics-informed neural networks not to find an approximative solution or numeric solution of a solution, but to find actually an exact self-similar solution to a 3D Euler equation. In group theory, there's a group by Alexander Shefov and many other, actually, we've seen examples this week for pathfinding for lab graphs, on Cayley graph in particular, and many, many other fields. So I hope that by now you are convinced, if you weren't already, I guess you were already, that AI is already useful in the practice of mathematics and can help solve difficult problems. And in the examples I showed, the goal of the AI is really to be trained to give you an intuition that is better than the one you would have had as a mathematician. And of course, with this augmented intuition, it bypasses the difficulty of the problem. All right, so, but in these examples, the AI is still used not as a tool, not as a reasoning option, and you'd like to know whether the AI could reason and prove a mathematical result on its own. So this is the second part, and I think I entitled it "When will AI prove theorems?" But actually, it's a wrong statement, because AI is already proving small theorems. The question is when AI will prove useful theorems from a research point of view, and it's probably not as far as we imagine. It's a much harder problem, of course. It's kind of a shocking question from a math point of view, at least from my point of view, because it kind of calls into question our very vision of mathematics. It's also a science fiction, either dream or nightmare, depending on the point of view. But that is, in any case, probably closer than we imagine it. So, if I were to ask you, can you train an AI to give a proof of a mathematical statement? And if you're done trying ChatGPT, you might think that you're going to train your own ChatGPT to do this. This is something that was tried, I think, for the first time in 2020 by Stanislas Paulu and Ilya Sutskever. Just as you probably all know, because we're in the Bay Area, but Ilya Sutskever used to be the chief scientist of OpenAI, the one who was involved in the drama when Sam Altman got fired. But mostly, he's an extremely brilliant researcher. Someone working in OpenAI told me he's the Oppenheimer of our generation. I think the choice of Oppenheimer is quite strange, but it means it's a very good scientist. So this is just to illustrate that this question has been here not only since 2022, but has been here already before, since people started to think that they could use deep learning to prove theorems. So how would you do? Well, what does an autoregressive transformer do in a nutshell? Well, very schematically, if you have a transformer that is trying to autocomplete a sentence, it will take the sentence, thanks to the training, sample density or probability of the next, get the density or probability of the next word, sample the next word or next token, then put it back, this is the autoregressive part, and do the same with your next part of the sentence. You sample your density or probability, you sample the next token, here's the comma. And because if you trained it on the internet, because this sentence comes from the Shawshank Redemption, the movie that is #1 on IMDb, it appears at many places on the internet, and so the more your sentence will look like this, the more likely your density probability will be spiked over the next word of this sentence. So you might eventually end up getting something like this. Here, if you have a full stop, for instance, it will tell the model, okay, this is the end, this is just the last step. And then it will output your sentence. Well, you can try to do the same with math and say, okay, now I have a statement. Instead, so density of probability, not of the next word, but of the next theorem to apply or the next step of the proof. Then you put back the step of the proof in the stack. And then you do the same, sample again, step of the proof, and so on. And you hope that at the end of the day, you have these statements, a stack, and then the neural network is going to say, I feel like here it's the end of the proof, outputs end of the proof, and then you take the right column, and it's the end of your proof. So this is essentially the very first and a bit naive way of thinking about it, but this is the first thing we tried nevertheless. A slightly more involved, slightly better way will be that if you work in formal language, in Lean in particular, but it will work in Isabelle, in Coq, you could have a statement, sample density or probability of the next step, you sample the next step, then you apply the step to your state. Then, thanks to Lean, you get the state, so you had this, you apply this theorem. Now you have, this is your new state, so you have two things to show. And then you try again, right? And so at the end of the day, if you do a good job in it, Lean will tell you you have nothing left to prove at some point, and then you don't even need a neural network. I mean, if there's nothing left to prove, you just stop. And then you take the right column, and this is your proof. So this essentially, so it will more look like this. Now you are in Lean, then you have your GPT model, and the output's a proof. The hope when you're doing this is that by showing it enough examples, the AI will be able to learn to reason just by learning to predict the next step each time. So you can be pessimistic about that by thinking, mathematicians are never doing like this. Like just looking at the next step is a bit short-sighted for math proof. But on the other hand, you could also be optimistic, saying like, looking at the next token is a bit short-sighted to write an essay, and GPT-4o is not too bad at writing essays. In any cases, whether you're pessimistic or optimistic, it can only work if you have enough examples. And enough meaning sufficiently diverse and sufficiently numerous. And this is the main limitation. This is the main limitation. Why? Because we have very few data available, especially formal data. So of course, as we've seen since the beginning of the week, you have two ways of writing mathematics. You can write in natural language, informal language, and you can write in a formal language. This is, again, written in Lean. So this is where I'm afraid, because my number might not be correct anymore. So in any case, the order of magnitude is probably around 150,000 theorems, 1.8 million lines. Is that correct? So this is extremely large for a human. I mean, there's been a huge effort of the Lean community, and especially the Lean maintainers, to reach this point. I never know these theorems myself in my life, but for a human, for a transformer, for training a language model, it's relatively small. And so this is the limit of the approach. There's a paper by Fabian Glöckle of 2023 that's tried to do this on Llama, which says if you use only this approach, this is essentially what you can do. And you can see clearly the limitations there. So a second approach, a complementary approach, was to treat mathematics as a game, to use reinforcement learning, in other words. So this is something we did, so many groups started doing this. I'm just going to talk about the two papers we did with Guillaume Lample, Marianne Lachaud, Thibault Lavril, Xavier Martinet, Gabriel Ebner, Aurélien Rodriguez, and Timothée Lacroix. I'm just saying out loud the names just to realize that it took us 2 years and all these people with 5 of them full-time just to get something. So it's of course something much more complicated. The motivation is that is definitely the fact that DeepMind released in 2017 an AI that was able to play chess against itself and be better than any human on Earth within 3 days of playing. And we thought, let's do the same with math. You train an AI for 3 days, it's better than any mathematicians on Earth, and then let's take vacations. So what's the game we want to play? It's this one. You have a statement. You apply a theorem. So making a move is applying a theorem or applying a step of the proof. So you make a move. You have the assumptions to satisfy now. So you make another move here. It's good. You make a move here. You have assumptions to satisfy. You make a move, nothing to show. You make a move, nothing to show. If you have nothing to show at the end, you won. That's how it works. So a fascinating game that we are all playing here. There are a few difficulties, though. The first one is really a machine learning difficulty. When you have a two-player game, you can have many very bad models. You make them play chess against each other. At some point, one is going to win. And so you know that this way of playing is better than this way of playing. And it gives you some feedback you can train again. Now you're starting with math. You have models. They've never seen math in their life. They're extremely bad. You give them a simple exercise. They all try. None succeed. You have nothing to train on. So you can't start from zero. This is really a non-trivial difficulty at first. The second one is that in chess, when you play, when you make a move, you still have only one chessboard, right? I mean, you just move the rook, you have one chessboard. In mathematics, it's a bit different because if you apply a theorem, then now you have the assumptions to satisfy. And so if you explore your graph of possibilities in a not a very good way, you could end up with a too large number of statements that you would like to show. And even if they are very simple, you might just saturate in memory for bad reasons, right? It's really a machine learning reason. It's really not a math reason. The two others are deeper. I think the first one is that it's extremely good it's extremely difficult, in mathematics to know how close you are to finishing a proof, except when you have already done all the critical steps, right? So in chess, at least you have some heuristics, right? You can count the number of points on the chessboard. So it's likely going to be much easier to train something to guess how good or how likely you are to win in chess than in mathematics. And of course, the last one is that the number of possibilities at each move in mathematics is usually much, much higher than in chess. So just to justify myself when I show what follows, because we haven't been able to fortunately, to train an AI to be better than any mathematician in just 3 days. All right, so the way we're working is the following. This is a classical proof search. I mean, it really looks like, I can talk about this because this is a thing I done, but it's probably extremely similar to what AlphaProof did. So you have the classical proof search work as follows. You have first, you're looking at a statement and you represent all the possibilities from this statement as a tree, right? So each different vertices is just another move that you applied, and then you have all your possibilities. Of course, you can't enumerate this tree, right? You can't even enumerate the first step. It's too large. So you try to explore this tree in a smart way. So the first thing you're going to do is go to select a path to leaves that aren't explored yet. Then you're going to try to use the first transformer, something that was trained in supervised learning, like a ChatGPT for math, to give you some intuitions of what are the possible next steps that will make sense. Then you're going to see what happens if you apply them. And for instance, if one of them is already solved, then you can say, okay, this was solved. I put a score of 1. If not, you will train another model to predict how hard it will be to prove these statements, and then you backpropagate the score, and so then it gives you a score in your graph of what is a good way, or what is a good path, or what is not as good path. And of course, when you succeed in doing something, then you use this data to train again your two models. So you train continuously, and you hope that it's going to improve and improve and improve at the end of the day. So what can you do with this? This was a paper that is now nearly 3 years old, so it's already very old in the field of automated theorem proving. You could prove 30 to 60% of middle school, high school exercise up to Olympiad levels, depending on the benchmark you're using, and a few exercises from the International Mathematical Olympiads. For instance, this is an exercise from the dataset, 7 never divides 2 to the power n plus 1. So it's a good exercise. I can wait 3 minutes to see if you want to do this. If you don't find the answer, I can give you the answer provided by the neural network. You see, it's not very long, actually.
Like the one from 80 years old, in 1960s.
Yeah, this one is one of the easy ones. I agree. Yeah, gosh, usually people complain that it's already too hard, and you complain that it's too easy. I'm very happy. Right. A funny thing, because we'll say in the morning, and it's good to say funny things. Out of these people, Guillaume Lample and Timothée Lacroix, right after this, so they created a model called Llama that you might know, but right after this they founded a startup that is called Mistral AI, and is so 2 years later it's worth 6 billion. So you see, if this is not an incentive to do AI for math, really, I don't know what is. So what's next? Well, there has been a lot of so because it's a solo game, you need a good base supervised model to start with, right? You can't start from zero, and you need something good to start with. And one idea that many people had, and that is already a hot topic in the area, is to get more formal data by training a model to translate from the proof that we have, like the natural language proof, the archive if you want, and verifiable data, formal data, the one that you can actually find in Lean, currently done by strongly skilled mathematicians that work in formalization. So I think it's from a mathematician point of view, it's good because it's going to help to train AI models, but it's mostly good because you will be able to formalize things more quickly, and so you will be able to check the correctness of new mathematical theories, and you can hope that at some point the entire math community will actually turn to formalization because it will be easy to formalize something, and we will be able to actually check our new theories or our new articles, right? I mean, if you can, in an ideal world, if you have a paper on archive, you can put it directly, automatically in a formal language and check whether the proof is correct. That will be great, right? Because we know that there are many papers in math that contain mistakes. For most of them, we haven't spotted them, most likely. And we don't know whether the mistakes are a problem or not, but we're still building new mathematical theories on these papers. And it can happen even in very good journals. Those are one of the famous examples are those two papers from 2004 and 2006. They are both published in Analysis of Mathematics, and they both exactly contradict each other. They can't be correct both at the same time, right? You have a quasi-projectivity of moduli spaces of polarized varieties, non-quasi-projectivity of moduli spaces. So really, they can't be both right at the same time, and I think none of the two has been retracted so far. So I wouldn't. Last year? Okay, so now I'm extremely curious. Is it the first one or the second one? Okay. All right. So you see, it's good to be able to formalize mathematics, to be able to verify what we're doing, because we're working in a field where almost correct is false, or almost correct is not true, at least not verified, and so you can't just be almost correct, right, in mathematics. You need to be rigorous. Today, we're very, very far from being able to do this. We're not too bad at doing a statement auto-formalization for a typical Olympiad exercise. So you give it the statement, it will translate the statement. Yeah, yes, of course. No, but that's why we're like... Of course. And this is a non-trivial question. It's much harder for the proof. Translating the proof is complicated because humans are making proofs that are essentially incomplete, right? You're not outputting every steps from a formal point of view. So we are very far from research level mathematics, but there is a lot of momentum in this field. So I'm pretty sure it's going to improve very quickly. All right. So just to say to conclude the talk, that this is a very fast-moving field. So I think it's good to be interested in it. I tried to represent here what, in my opinion, were the interesting methods given in different years, like and what the AI models could prove these years. So in 2019, this was taken from a research paper, so this is not a joke. This was essentially what you could hope to prove with a trained neural network. Like, okay, I'm pretty sure it's one line in Lean, right? In 2022, you could start to prove things like these ones. In 2024, as you've probably heard of, AlphaProof got a silver medal at the International Mathematical Olympiad. They were just 1 point from the gold medal, so they are getting much better. And you see that the number of methods, of highly relevant methods of this year, are improving a lot. Here, there are probably much more in 2024. It's just that it's too large for the slide. So you really have an exponential growth of this kind of interest in this field. Today, there are new approaches. So this is 2024, and what I presented is already kind of old school. Now there are new approaches, post-2024, using approaches that looks like end-to-end reinforcement learning, which is essentially what was used to train the reasoning models, the so-called reasoning models in formal language like O1, O3, and DeepSeek R1. All right, so this is it for me. I hope I convinced you that AI methods are useful in the practice of mathematics. I'm talking essentially about LLMs, but I think the LLMs will probably not be the final AI tools that will be used. It's just the best that we have so far, but let's see in 5-7 years. I'm convinced, for one, that the practice of mathematics will probably change, and I think that's okay, right? There used to be a time where in the practice of mathematics, a non-negligible field was to try to find the digits of pi. With computers, it has become easier, and that's good. We focused on something else. I mean, so I really don't think that AI will replace mathematicians. I think, like most people presenting this week, that it will instead enhance them. And on this, I thank you very much for your attention.
Questions?
For the purpose of verifying bigger research, what are the correct heuristics to look for in the
So sorry, I'm not sure I heard. Okay, so you were. Can you say it one more time? Sorry.
Yeah. So for the purpose of verifying what's previous math research, if we want to be whole group auto optimization from the bad, what are the correct heuristics that we should be looking for when training these auto optimization?
Okay, that's a very good question. So it's so for the purpose of formalizing the proof, what are the correct heuristics that we need to look for? So I think like the question of I'm not sure it's that much about heuristics rather than the purpose of formalizing a proof. I think is extremely close to actually being able to prove something, because you could imagine that the human proof is essentially a sketch of the formal proof. So already translating this informal sketch into a formal sketch is not completely trivial. But then you still have holes, and you'd like to prove them. And in this case, you will need a prover that is already trained to try to fill in the gaps in Lean. So that will be one way of doing. Of course, in some cases, it's a bit too optimistic. But you can hope that at least you could start like this, get more data, and then when you have this, you can train your prover again to be better, because now they have more examples. And with this game, you could, the ideal will be that it kind of, by iterating, it just improves, and then you will be able to have more and more proofs. In any case, you need to start with something, and starting with something is right now Mathlib, but you might want to have other examples, so the beginning is quite costly.
So you described how you're using a proof assistant to create a sort of reward mechanism so you can use reinforcement learning to train a model to write proofs. And then in the conclusion slide, you seem to suggest that something similar is going into the so-called, learning model, like O1 and DeepSeek and all that. And my impression was those architectures are quite different. So I was wondering, did you need to say that those are trained in an analogous way or not?
So they are. So the question is the reasoning models architecture is quite different from the one I showed before, where we were using execution of the proof assistant as reward for the reinforcement learning. There is a common point, though, so it's indeed relatively different. But there's a common point, which is that you still have a proxy of correctness at the end of these models, where you try to have something that evaluates whether the proof is correct or not. Of course, it's not as good as with a proof assistant, because you don't have something that says the proof is correct or the proof is incorrect. What you have is usually trained on problems, that is the part I've seen, trained on problems where they try to have closed form solutions, like solutions that you can only get with reasonable probability if you had the correct proof. So it restricts a lot the math problem you're training on, but at least it gives you a relatively reliable feedback or reward that you can use for end-to-end reinforcement learning. And of course, it's only a proxy, but it's better than nothing. That would be great to be able to do this with Lean informal language, but precisely because we don't know how to auto-formalize, it's extremely hard to do. But I'm sure there are many people researching in this direction. At least that's my take on it.
Have you tried reverse engineering or interpreting what your transformer is doing to actually find the Lyapunov functions?
So yes, probably not enough for the Lyapunov functions, because we oh, sorry, yeah, my bad. So did we try to reverse engineering what the transformer was doing in the first part to find a Lyapunov function? To try to attack the transformer to understand what's going on behind. So for the Lyapunov function, we should have tried more. To be fair, we tried 1 week, so that wasn't enough. And we didn't find anything super relevant, but there might be something. But it was tried with the same approach on other problems that are simpler, like, for instance, François Chaton's work on predicting GCD. So GCD numbers, you try to understand, try to predict the GCD between two numbers. And in this case, you can interpret quite impressively what the transformer is doing. There are jumps in the accuracy or jumps in the loss, if you want, and the jumps actually correspond to some groups of numbers that shares common divisors. So you can actually understand this. There was another example, I think, which is on predicting autonomized family of eigenvectors for symmetric real matrices, I think, where you have jumps, and some of the jumps you can interpret. Most of the time, you do have jumps in the curve, which is that the model understood something, and you don't understand what this something is, because it's not the same path as what human will do. But in these cases, it was the same path, and I think one of the jump was like norm is equal to 1, or it's quite surprising that it actually corresponds to something. So.
I just think that following up on Chaton's work is actually possible to the student here to train a model to find the Vesu coefficients, to find a proof that the GCD is correct.
Yes. No, yes. For the GCD part, the goal was just to understand what the transformer was doing.
I'm saying
okay.
that there is a way.
Okay.
So just following the paradigm that you said, by giving examples of Vesu coefficients in addition, you can train a model to.
Okay.
But furthermore, that you can actually prove some convergence theorems. That if you were able to generate, according to your language, proofs that are similar to questions that are similar to the distribution of what your test is, under that assumption, then you are also able to find those proofs.
All right. So indeed, that's a more complete answer than the
No. I mean, it's exactly the same framework. But the assumption is that the distribution that you're generating is the same as the test one. It's just you're going backwards.
Yes. Yes. For the GCDs, I don't exactly remember for the GCDs. I remember that the distribution played a large role, and at the beginning, just trying a uniform distribution was a bad idea because it wasn't a uniform distribution of the GCDs.
Okay, maybe one last question.
So to what extent do you think that generating synthetic data could be helpful for theorem proving?
I think it used to be extremely helpful before the open weight model, because people were retraining from scratch large language models. And so in this case, you are wasting your first coefficients just to learn a structure from random weights. So in this case, the synthetic data was like a cheap way of doing it, and then you will fine-tune on more expensive data or better data. Today, I think it could still be very interesting. The only thing is that because it's more templated, there's some non-negligible engineering about how you are making these synthetic data. In particular, because if you're just starting from a statement and then applying theorems at random and see where it leads you, and then take this as your theorem, usually what you will get is something much simpler than one human will do, and very off distribution. There's one exception that is in plane geometry, where there was a very nice paper, the paper of alpha geometry, that showed that actually doing this was giving meaningful examples. But I feel like in most fields, it will give examples that are completely off distribution. If this is what you meant by purely synthetic data.
Yeah.
There's